dual gas law, P equals nRT over V, okay? It's our ideal gas law. And remember, the entire formula is more like PV equals nRT, right? But you take that formula and you format it to what you're looking for in the problem. In this case, since we're looking for pressure, that's why it's that way. But you can find the ideal gas law written in different ways based on what is being solved for. But when you have the PV equals nRT, that's like the basic, you know. Okay, so that's our formula that we're using. So think about it. So we have volume, okay, check. We have T, check. We have R, just because that's, you know, it's a consistent number, check. And then N, moles. We don't have that yet, right? So we need to start by converting. I'm just going to go ahead and call this number 1. You know, we don't, yeah, we already wrote the number 2. Okay. Just keep track of them. So we want to start by converting. So I have number 1, which is the sulfur hexafluoride. And remember with that, let's see, we have the 14.9 grams. I'll also underline this one. So we have the 14.9 grams of sulfur hexafluoride. Remember, we want the grams to cancel out, so that means that we have to divide. 1 gram's on the top, 1's on the bottom, they cancel out. And let's keep track here. So this here shows us this is 3 sig figs, and we're not counting the molar weight. For sig figs, that is. So do 14.9 divided by 146.06. That number we get is 0.271. There we go. There's a number. Then we convert it to sig figs. It's 3. There we go. So that's how many moles of the sulfur hexafluoride we have. And remember, we write down the whole number in this case because, you know, I predict we're going to need this later. You know what I mean? Unless you know for certain this is like your final answer, then just write the number you originally got, you know, before rounding. I've just found it saves some time if you ever have to go back and use that number and didn't think you were going to need it, you know. Anyway, so now we're on to the sulfur tetrafluoride. 3.73 grams of the sulfur tetrafluoride. So that's another one where we have 3 sig figs. And then we put, once again, molar mass on the bottom, make sure the grams cancel out. Then you do the calculator, 3.73 divided by 108.07. We get this number. Okay. And then we do 3 sig figs. There we go. And just remember, this 0, even though it comes out after the decimal, it's not significant yet, you know. If the 0 was after the 5 here, it would be significant, but it's here where it's before, it's not significant yet. Okay. So that's just what we're going to keep in mind. So we're also just going to make sure we remember that's how many sig figs. Okay, so now we have our measure of how many moles are for each. Okay, so now we have that N value that we need. So now we can actually solve for the pressure. Okay, give us some more space. So we'll find the pressure of 1, which is the sulfur hexafluoride. So we'll do P1. There we go. That's where it comes in. And then we do N. Remember, you want to use the full value for this. And write the units, because it just helps to make sure, you know, that your units cancel out as, you know, they're supposed to. Some people don't. And then they go back through the problem and they're not sure, where did I go wrong? You know, that's where you went wrong. That's where you went wrong. Oh, fuck, I hate computers, man. Come on. Okay. Fuck, dude. Okay. Give me what I want. Oh, just let me move it. There we go. Got it. Great. Stay. Oh, fuck. Okay. We're just call that good. That's it. That's how it's going to be. Okay, so now remember, so we go N, R. So we want that value for R. Might take me a second. 0.08. Come on. 0.08 20574, 20574, 20574. Bam! We have the liters times the atmosphere and then mole times Kelvin, okay? So that's NR. Now we have T, which we already converted to Kelvin conveniently. There we go. And then just, make sure the sig figs are here. So, this one's 2. This one's 3. And then R, as we mentioned, is, it's an exact, so it doesn't factor into sig figs at all. There we go. Okay. And then on the bottom, we have volume. So in this case, we have the whole volume of the tank, which is 7.00 liters. I'm also going to say this here. If you have a problem where the volume changes, like for example, a problem where you have one container filled with something, you have another container filled with something, and then you open like something between the containers that lets them interact with each other. If you found the pressure of each of those containers before you open them to each other, the pressure of those containers is going to be different than the total pressure. You can't just add those together because the volume changed. One of the things that you used to find the pressure of each of those containers, as I said, has now changed. The volume isn't the same anymore. So from what I know, you would need to recalculate the pressure for that new volume, and then you can add those together to find the total pressure, So you got to keep that in mind. When we're solving this here for these problems, we're assuming, or based on, actually, we're not even assuming, the problem states it's all in the same tank, right? But if a problem tells you something like that, where they're like, we measured the pressure of 2 separate containers, and now we're combining those containers. You can't use this same method of solving because, as I said, the volume's different. So the individual pressures of each of those components will change. Okay, anyway, back to what we're doing. That just, helps out, right? And remember, we're doing multiplying, dividing here, all the same rules. So we're going to end up with 2 sig figs just because of how it is. It's like that because that's how it is. I'll have to figure out where that's from. Okay. 0.12871 times 0.082057 times 280.05. Okay. Divided by 7. Okay. So I have that answer. 0.96231. Okay. Proper sig figs. Remember, it's 2 sig figs. 0.33. Okay. And that is, if I remember correctly, that is our pressure. So that would be in atmospheres. There we go. Okay. Because I've already done this a lot, so I know that this is right. But what you want to do when you're doing this, to just double check, is you go, okay, do my moles cancel out? Yes, they do. Okay. Do my liters cancel out? Yes, they do. Do my kelvins cancel out? Yeah. Okay, you're left with atmospheres. And that atmosphere there, that's the unit for pressure that we're using. So as long as atmosphere is left, then you know it's correct, okay? It's now on to the second one. Give me a little more space. Hopefully this document doesn't end up being like absurdly large. Okay, so now we're finding the pressure of the second one, right? So we want to take the moles. If I remember correctly, this is the sulfur tetrafluoride. And remember, we want to use the full value. And that is 3 sig figs. So now luckily, all these values are the same in this case. Again, same container, same conditions. Makes it nice and easy. Same value for R. And just remember to include those units again. Okay. Remember, there's 3 units for the liters there, and then 2 there for the temperature. Okay. Now we'll do my calculator stuff. Okay. 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 Okay, so we'll make sure we write it down as atmospheres, okay? And then we know that we want it in 2 sig figs just based on those rules. So that would equal 0.11 atmospheres. Okay. So that's the measure of the individual pressures of each of those gases. And now the cool thing about the law of partial pressures is that as long as it's a constant volume, constant temperature, this works. You just add the atmospheres together, you add the pressures together, and then there's your total pressure. You're done. Okay, so we add those together. That's 0. Oh yeah, remember, you want to use the whole one. The whole numbers. That's going to take me a second again. Okay, and then it's 2. So this is so I'm going to say this right now. This is our final answer. So we're not going to write the whole number. We're just going to write the one rounded to 2 sig figs because we know this is our final answer. Our questions already told us we don't have to do anything more with this. This is our last answer. Okay. 0.4, and then in the actual stuff it says 0.4482, on and on. But because of that digit here has an 8 next to it, that means we round up. So that next 4 becomes a 5. So total pressure, I want to write that here. Total pressure equals this number, okay? So that's how that works. So yeah, I don't think I have another problem. Yeah, so that's it. Okay. So to, recap, we have the law of partial pressures tells us under, constant temperature, constant volume, to find the total pressure of a mixture, you add the individual pressures of the components together. And there you go. There's your atmospheres. And to do to find the pressure of those individual gases, use the ideal gas law, which is here. And all this stuff you convert where necessary. And yeah, so that's it. That is the law of partial pressures and how it all works.